Hey guys, welcome to the lesson on performing operations with complex numbers. So this is our introduction lesson to complex numbers. So before we get started, we had a little do now that we wanted to work on in class. Let's go ahead and just add two binomials. So this is just a simple arithmetic of binomials. So the way I kind of went over this is if there was a negative in front of this parenthesis or this binomial, we would distribute it. Since there isn't, we just drop the parentheses and we get 1 plus 2x. Again, if there's anything to distribute, we should distribute, else we just drop the parentheses and we're left with plus 2 minus x. If we combine like terms, here's my 2x, my minus x. We can combine those together and combine our numbers, our integers, and we actually come up with x plus 3 as our solution. So we have 1x and 3 integers. So now let's do the subtraction one. For the subtraction one, again we distribute if there's anything in front. There isn't, so we're just going to drop the parentheses and have 5 minus 5x. This one has a negative, that's the same as say negative 1. So we're going to distribute that negative 1 to both of these terms inside my binomial. When we do that, we get minus 2 or negative 2, and then negative 1 times negative 3x gives me plus 3x. Again, I'm going to go ahead and combine my like terms. So I have this negative 5x plus this 3x. When we combine those together, we end up with 2x, and when we combine our integers, we end up with 5 minus 2, which is just 3, and that's our solution. The final one is just to distribute. We're going to distribute this 3x to both of my terms inside my parentheses, or inside my binomial. We get negative 18x plus 3x squared. If we were to write this in a standard form, this would give us 3x squared minus 18x. And this would be our solution. So again, this was just our warm-up to get us into the right state of mind when it comes to working with these imaginary or these complex numbers. Our objective for this lesson is given an understanding of adding, subtracting, and multiplying binomials. Students, meaning you guys, will investigate properties of imaginary numbers and perform operations with them. So let's go ahead and just kind of fill in the blanks. Students will look at properties for complex numbers and perform operations. So that's what we're doing. Let's jump straight into defining what an imaginary number is. So an imaginary number is a number represented by I, and it is equivalent to the square roots of negative 1. So before we said that there were no roots, or we did not get a solution whenever we came across a negative square roots or a negative discriminant. In this case, we're actually going to define it as an imaginary number. So it's true that these numbers do not exist in the real number line. So if we look at our general Cartesian plane, we have an x and a y axis. Our numbers would not exist, our imaginary numbers do not exist in this plane. However, they do exist, as we'll see in the next lesson, in my complex plane, meaning this instead of x is going to be all my real numbers, and this instead of y are my imaginary numbers. So on that note, let's kind of begin by defining all of these imaginary numbers. So the first one we define is the square root of negative 1. So I is actually equivalent in value of the square root of negative 1. Now if you punch that into your calculator, you notice you'll get an error signal or an error sign. That's because the calculator is giving you numbers from the real number line. It does not know how to differentiate between imaginary and real. However, let's go ahead and prove this case with the rest of them. So we kind of talked about this in class a little bit, and this is again just a review. So if I is equal to square root of negative 1, then I squared is equal to I times I, which in turn is just square root of negative 1 times the square root of negative 1, which if we remember that just cancels out, or it's the equivalent of saying the square root of negative 1 squared. So this whole quantity squared. When we get that, we notice that this cancels out. My square cancels out my radical. So what we are left with is negative 1. So what we just showed was an algebraic proof for the value of I squared. I squared is equal to negative 1. So let's go ahead and see if we can define the pattern. So I would be given to me as, again, let's just for argument's sake just call that I. It's the same as you would call 5. The value of 5 is equal to 5. The value of 6 is equal to 6. The value of 20 is equal to the value of 20. So we're going to say the same thing here. The value of I is equal to the value of I. So let's go ahead and continue with our pattern. We know then, we've proven that I squared is equal to negative 1. So we're going to write that as negative 1. I to the third power is just I squared times I. In turn, that gives me negative 1 times I, which is just negative I. Again, please make sure to pause this and rewind as many times as needed so that you can make a little bit of sense out of this. The next one we have is I to the fourth power. Well, I to the fourth power can be written as I squared times I squared. Again, our exponent rule says that we just add our exponents when we're multiplying. So this in turn is equal to negative 1 times negative 1. Well, that's just a positive 1. So you can see these are the terms that I care about. This one, negative I, and 1. If we rewrite the pattern, we notice that I to the fifth power is just going to be I fourth, which is 1, times I, which in turn gives us I. This one's going to be I to the fourth times I squared, which is just negative 1. I'm sorry. Yeah, negative 1. That's just going to be 1 times negative 1. The I to the seventh is going to give me negative I. The I to the fourth will give me 1. And it just cycles these four values over and over and over. So you guessed it, if I had I to the 9th, I to the 10th, I to the 11th, and I to the 12th, again we would cycle through these numbers, meaning this would be I, negative 1, negative I, 1. So with a little bit of practice you'll get better at these. But we're going to see, really for this lesson, we're going to just talk about I squared and evaluate that out. So let's go to our first example. Our first example is to solve for x. So by now we've looked at 4 different ways for solving roots or solving for x. There is the square root method. There is the factoring method. There is the completing the square. And there is the quadratic formula. So you can pick any one of these methods to solve this. Well, this one just seems to be an easy case of square root. So we're going to go ahead and square root both sides. And remember, when we square root one side, we have to square root the other. So what we do to one side, we do to the other. When we get this squared and this radical cancel out, but on my right-hand side, we're left with positive or minus, and minus. This then simplifies to x squared is equal to plus or minus the square root of negative 24. Well, if we remember our product property rule, we can actually break this up into products of or factors of negative 24. Oh, I'm sorry, I made a mistake. This shouldn't be squared. There we go. We're going to break this up into properties of negative 24, or some sort of factors of negative 24. So we get x is equal to plus or minus the square root of negative 1 times the square root of 4 times the square root of 6. If we do this, we can then just evaluate, and we get plus or minus I. There's our first value, square root of negative 1. Square root of 4 is 2, and the square root of 6 remains the square root of 6. We can't factor that further. If we were to write this in standard form, and we'll define that in a second, it's plus or minus 2i times the square root of 6 would be our solution. We obtain 2 solutions. Solution number 1 is a positive 2i root 6, and solution number 2 is negative 2i root 6. Those would be our 2 roots. And again, those roots are imaginary solutions. So let's take a look at what a complex number is. So a complex number is a number with an imaginary element. Complex numbers are written in the standard form as a plus bi, or sometimes a plus or minus bi, depending on what your number is. So this means that a and b have to be real numbers. So a quick example of what this means is that an example of a complex number can be a is 3, and b can be a 4, and I remains I. So, or another one would be 5 minus 2i. So again, this component is real, this component, or this value is real, 3 and 4. Same here, this value is real, and this value is real, it's negative 2. We were to break it up, we have that this becomes our real component, and this is our imaginary component. So again, this is my real component, and this is my imaginary component. So let's take a look at this grid. It's going to actually break it down for us fairly easy. If we look at any number, any complex number, let's call it b plus bi, a plus bi, when both a and b are not 0, so this a can be any number like in the top, and this b can be any number like in the top, we come up with a complex number. So this gives us a complex number. Now in an example where b is not equal to 0 but a is, that means that a would be canceled out and we're just left with some bi. Well, if it just has this imaginary component, then this is known as pure imaginary. It's a purely imaginary number. Now let's go back to our example again and apply some other the other rules. So if b is equal to 0, now this is going to go away and a can be anything. Well, we're just left with an a component, and again, if we look up here, that's just the real element. So this is 100% real number. And the very last one, when a is equal to 0 and b is equal to 0, both of these go away. Well, we have no value, that's just a 0. So again, this little graphic organizer allows us to easily understand what our complex numbers are, pure imaginary numbers are, real numbers are, and when we have a constant at 0. With that said, we're going to define addition, subtraction, multiplication, and division. Division, we're actually going to concentrate on it in a different example. For the sake here, I'm going to show you quick examples. When we mean addition, we can say, well, that's like 3i plus 2i. Well, again, we're just going to add our i's together. We get 5i's in total. If we look at that example again, this time with subtraction, we end up with just 1i. So all we're doing is combining like terms. So it's very similar to what the do now was about. We just combine our like terms, our x's and our integers. Same deal here. For multiplication, we get, let's give it an example like 3i and maybe i plus 2. Again, we're going to have to distribute to both terms inside our parentheses or our binomial. We actually get 3i squared plus 6i. But if we recall, I squared is equal to negative 1. So really we get 3 times this negative 1 value, because I squared is negative 1, plus 6i. If we simplify that, that's just negative 3 plus 6i, and that becomes our solution. So there's more to it when you're multiplying. Multiplying seems to be the harder of the three. Division, we'll take a look at that as its own example in a bit. So let's go ahead and cut to example 2. When we're looking at example 2, we're going to go ahead and write in standard form, meaning we're just going to add these complex numbers together. So again, if there's anything in front of this parentheses, we distribute. Otherwise, we just drop the parentheses. There's nothing to distribute. This positive, you can distribute a positive 1 if you want, but that's just 1 times positive 5 is positive 5. 1 times positive 4i is 4i. At this point, there's nothing tricky but combining our like terms. So we have a positive 4i and a negative 4i. We have these integers, or these real components. When we add them up together, we end up getting 13 plus 3i as our solution. So it's 8 plus 5 is 13, and then our imaginary solution in the back. Alright, let's take a look at the next one. We have 8. Again, there's nothing for us to draw or to distribute inside of this parenthesis. So we get 8 minus I. This one, however, we do have to distribute to this negative 1, or this negative term, to both of these numbers inside our parentheses. When we do this, we get negative 5 minus 4i. Again, if we were to combine our like terms, this is our I value and this is our negative 4i. When we combine our I values, we're going to get negative 5i, and 8 minus 5 just gives me positive 3. This is not written in standard form, which means I have to rewrite one more time as positive 3 minus 5i, and that becomes our solution. So again, please pause and rewind as needed for this section. We gave you an example of 3 different ways. So the only one here I really want to try is this multiplication problem. I'm going to go ahead and just distribute to show you guys again the distribution. When we distribute to both elements, to both values inside a parenthesis, we end up with 6 times negative, 4 times negative 6, there we go, or 4i times negative 6 is negative 24i, and then 4i times I is 4i squared. I'm going to bring these values here just to show you guys a little bit clearer. That really just gives us negative 24i plus, don't forget the square, this 4 and I squared. Well, this whole I squared, remember, is just negative 1. So if we rewrite that as negative 1, we can kind of go ahead and distribute that out. So our solution is actually negative 24i minus 4. If we write this in standard form, we get negative 4 minus 24i. That's our answer. So again, just another multiplication problem. Then we're going to go over the concept of complex conjugates. So a complex conjugate is a number that eliminates the imaginary part of another number when multiplied. So for instance, we're going to see in the next examples for divisions, we don't want any complex numbers in our denominator. So far there's 3 things we don't want in our denominator. We don't want a 0 in our denominator, we don't want a fraction in our denominator, we don't want a radical in our denominator. Well, the other one we don't want in our denominator, they're going to be complex numbers. Oops, that is not a complex number. We'll say 2i. We don't want complex numbers. So in order for us to get rid of that, we're going to have to find a complex conjugate. So this complex conjugate is really, we're just multiplying, our real element stays exactly the same. The only thing that's changing is our imaginary term. This and this term is negative, but we want that to turn positive 3i. That'll guarantee that when we multiply them out, the imaginary elements cancel out. So let's take a look at the last 2 examples. That's going to be 3 minus 2i, and this one would be negative I, or when it's just purely imaginary, you can multiply by its imaginary component and you're good either way. So just for practice, I suppose you can use the negative terms. So let's take a look at when this comes into play. Here we have an example, 7 plus 5i over 1 minus 4i. Again, we don't want this imaginary, this complex term in our denominator, so we're going to have to multiply both my numerator and my denominator by this complex conjugate. So in our denominator, my complex conjugate is actually going to be 1 plus 4i. But when you multiply a number in the denominator, you have to multiply in the numerator. So I'm going to multiply that same exact number. When we work this problem out or multiply across, we end up getting on top the quantity of 7 plus 5i times 1 plus 4i. In our numerator or our denominator, we end up getting 1 minus 4i, that looks like a 9, 1 minus 4i times its conjugate, 1 plus 4i. This then just becomes multiplication. You can use FOIL, box method, you can stack them up. However that you've been taught to multiply is okay, as long as you keep combine all your terms at the end. So for this case, I'm going to use the box method. I believe you guys are fans of that. So if I use my box method, on top I'll have 7 plus my 5i, and on the side I'll have 1, 4i. When I multiply these out, we get 7, we get 5i, we get 28i, and then we get 20i squared. Well, remember that my I squared is just -1, so really this value is -20. So we're going to go ahead and now combine our like terms. We get 7 minus 20. Those are like terms. So when I combine those, that just gives me -13. And then I'm going to combine these terms, my i's together. When I combine them, I get 28 plus 5. That's 33. So plus 33i. So our final solution in standard 4 is -13 plus 33i. Let me actually write that in red just to be consistent. Plus 33i, and that would actually be our answer. Now let's do my denominator. So I'm going to do these in two sets, or color coded so you can tell them apart. In my denominator, again, I have my box method. For my numerator, I have 1 minus 4i, and for my denominator, and for the other multiple is 1 and 4i. When I multiply my 1s, I get a 1. When I multiply 1 times -4i, I get -4i, positive 4i, and then right here I get -16i squared. And again, remember that this I squared is just -1, so really my value is positive 16. Again, I'm going to combine my like terms. We know for a fact that here's a positive and a -4i. Those cancel out. So what I'm really left with is a 1 plus that 16, which in this case is just 17. So my final answer here, for my denominator, I'm just left with 17. For my numerator, I'm left with -13 plus 33i, and we're good to go. Alright guys, so that completes the entire lesson. Again, it's just review notes. Please make sure to pause and forward and go about how you like. I hope this helps, and see you guys in the next lesson.